Hi, thanks for joining me. Today I have a fun number theory problem for you, and this involves the year 2021. So we have a sequence of numbers an with a1 being equal to 0, a2 being equal to 1, and then for n at least 3 we have an equals n minus 1 times an minus 1 plus an minus 2. So it's n minus 1 times the sum of the previous two terms. We want to find the 2021 term mod 2021. Okay, so if you want to have a go at this problem, pause the video now and give it a go for yourself, and I'm going to jump straight into a solution. Okay, so the first thing we're going to do is state and prove a quick lemma, and that's this guy here. An minus n times an minus 1 equals an minus 2 minus n minus 2 lots of an minus 3. So of course, because we've got an n minus 3 in our subscript, we need n to be at least 4 for this lemma to make any sense. So this I claim is true for n at least 4, and up here I've just written down the recurrence relation defining the an's. The proof to this is actually not too difficult. Let's quickly prove this. What we're going to do is just start from an, so proof, my pen is about to run out. We have an, just from this guy here, is n minus 1 times an minus 1 plus an minus 2. But of course, if we bring n lots of an minus 1 onto this side, we're going to get our left-hand side here. So then we can just work with the right-hand side and try and make it look like that. So if we bring the an minus 1 onto this, or n lots of the an minus 1 onto this side, we're left with an minus n lots of an minus 1. And that equals, well, here we've got n minus 1 lots of an minus 1. So if I subtract n from that, I'm going to be left with a minus an minus 1 like so. But then I've got plus n minus 1 lots of an minus 2. But an minus 1, I know what it is by plugging it into this formula here. I know that an minus 1 is simply n minus 2 now, lots of an minus 2 plus an minus 3. Like so. So literally just swapping all the n's in this guy for n minus 1s, I get this line here. But then I can just plug that into this thing here. So I get this is equal to minus an minus 1, which is then going to be minus n minus 2 lots of an minus 2 plus an minus 3, and then add on this n minus 1 lots of an minus 2, like so. Well, how many an minus 2's do we have? Well, we have n minus 1 minus n minus 2, and that's going to give us a minus 1 minus minus 2, which is going to be positive 1. So we have positive 1 an minus 2, which is what we have here. And the number of an minus 3's we have is minus n minus 2. So we've got minus n minus 2 an minus 3's, which is exactly our right-hand side here. So if we clean this up, we get the right-hand side, and that proves our lemma. So a very simple lemma with a very straightforward proof. Now let's use this to solve our problem. Okay, so remember our problem is to work out a 2021 mod 2021. And these are the kind of the two pieces of information we have so far. So the first line is just our definition of the an's, and the next line is the thing that we just proved. Now, we want to know a 2021 mod 2021, but just using the thing we've just proved, we have that a 2021 minus, so if I just plug in n equals 2021 into this line, so a 2021 minus 2021 lots of a 2020 equals a 2019 minus 2019 lots of a 2018, like so. So we have this thing here, and we notice that the left-hand side kind of looks the same as the right-hand side, except wherever we've got 2021 written here, we've written 2019, and wherever we've got 2020 written here, we've written 2018. So we're kind of subtracting each of these numbers by 2. But notice I can plug this back into my thing here, except now with n equals 2019 into this guy here, and I'll get that this thing here equals a 2017 minus 2017 lots of a 2016, like so. So essentially subtracting 2 from all the 2019s and then subtracting 2 from the 2018 just by using this formula here. And then I can do the same thing again on this guy, and then the same thing again on the next line, and so on. So I can in fact keep subtracting 2 from wherever I have 2017, and from wherever I have 2016 subtract 2 from that as well. So I can kind of continue this argument inductively until I arrive down to a3 minus 3 lots of a2, like so. So essentially what I've done is I've started off 2021, and I've shown from this line here that I can essentially take away 2 from the 2021s and take away 2 from 2020 to give me this line here. But then I can apply the argument again to get this line here, and then to get the next line, and notice that these numbers are decreasing, And I can keep doing that until A3 minus 3A2. Notice that I can't do another line of this, because if I did, I'd get to A1 minus 3 lots of A0. But we haven't defined A0, so we have to stop here. But what we have here is the same thing as A3 minus 3 lots of A2. But this is something we can go ahead and compute, because we know A2 is 1, and A3 we can just work out, using our definition, is just going to be 3 minus 1, so 2 lots of the sum of the two previous terms, so 0 plus 1, so 2 lots of 1. So that is, of course, just 2. So A3 is 2. So if you just plug that into here, we're going to get 2 minus 3 lots of A1, which is just 1. So 2 minus 3, of course, is minus 1. So we have A 2021 minus 2021 times A20 equals minus 1. So then, of course, if we just add 2021 times A20 to both sides, we get that A 2021 is equal to minus 1 plus 2021 A 2020, like so. But the key thing to this is we only want to know what A 2021 is mod 2021. So this thing here will vanish when we consider both sides mod 2021, because obviously each of the AIs are going to be integers. Perhaps that's something you should mention, but it's hopefully quite obvious that each of the AIs are going to be integers. So we have that A 2021 is congruent to minus 1 mod 2021, and that's our solution. I hope that has all made sense, and I hope you've managed to follow. Thank you for watching. I'll catch you in the next one. Have a great day.